2.1 intercepts, symmetry, and graphing. This is going to be a bit of an introduction to graphing, and then we're going to talk about symmetry, which is historically something that the course captain enjoys putting on our exam. So it's likely there will be a question about symmetry on this first exam and probably something on the final as well. So for finding intercepts, if I have an equation, and this applies for any equation, whether it's an equation of a line or a circle, the process is exactly the same. What I do is I set one value equal to 0 and I solve for the other one. So for example, if I want to find the y-intercept, I plug in 0 for x and solve for y. So it's usually pretty easy if it's written in this form of y is equal to something, because if I plug in 0 for x, well, that makes every term that has an x in it go away because it's 0. So 0 squared, 0, minus 3 times 0, 0, minus 4 is y is equal to negative 4. Now, something that's very important is that's not the answer. Don't write y is equal to negative 4 because that's not a point. When we're talking about intercepts, we're talking about points. And so since I plugged in a 0 for x, my point's going to be 0, negative 4. Make sure you're writing them as points. I'm going to be a stickler about that on the exam, and you will lose points if you don't write them in that form. Very similarly, for the x-intercept, I plug in 0 for y and solve for x. Now, sometimes that becomes a little bit more involved. Like in this case, when I plug in 0 for x, this actually becomes a factoring problem, something similar we saw in the first section or maybe the second section. So I want to factor this. I want to find two things that multiply to get me negative 4 and add to get me negative 3. Well, those two things are negative 4 and 1. Then I just set each part equal to 0, solve. I just add 4 to both sides for this first equation, and I subtract 1 from both sides on the next equation. And so I have, as far as algebraically, I have x is equal to 4 and x is equal to negative 1. But again, that's not an answer, so I need to make sure I'm writing my answer as points. So my x-intercepts are 4, and 4 comma 0 and negative 1 comma 0. And if we have a function, we will have at most one y-intercept. With x-intercepts, there isn't really a strict limit. You could have 0. There's a lot of functions that have 0 x-intercepts. You could have a million x-intercepts. So don't kind of think, oh, I think I should only have one x-intercept. If you're following the process correctly, you can have multiple x-intercepts. That's perfectly fine. Okay, symmetry. We're going to talk about 3 different types of symmetry. We're going to go through the strict definitions and then talk about how those definitions are helpful if we want to go through the process, but as far as the concept goes, it's not too terrible. So, definition for symmetry about the y-axis is that if I have a point, xy, or let's say maybe 2, 3 is on my graph, then negative xy also has to be on my graph. So if I have a point 2, 3 in my original graph, well, negative 2, 3 also has to exist in my graph. So here's a perfect example here. I have that's the absolute value graph. If I look at any point strictly, well, let's look, 2, 2 is clearly on the graph. Well, then negative 2, 2 is on the graph. And so that can be a little bit exhaustive, but it's perfectly fine if you have a graph to kind of just look at it and say, okay, I'm able to fold my graph over. If I take the right side of my y-axis and I fold it over on the other side of the y-axis, I will have that matching up. So if you have a picture and you have points, go ahead and go through the test. If not, you can kind of just examine it and say, okay, this is the requirement. This is what it looks like. These tend to be more true or false questions anyways. Very similarly, symmetry about the x-axis is if I have a point, the x negative y of that point has to also exist on my graph. So these aren't usually functions, but here's an example. Again, let's pick a point. It looks like 4, 2 is on my graph, and so is 4, negative 2. But again, visually, which makes a bit more sense to most people, is that I'm able to take the top part of my graph, fold it over the x-axis, and it's very important that it's going over the x-axis. I fold it over the x-axis, and that kind of it gets folded on top of the bottom part of my graph. Then finally, symmetry about that should be origin, symmetry about the origin. So if I'm trying to find symmetry about the origin, if a point exists, the negative x and negative y of that point must also exist on our graph. And so usually when we're talking about symmetry, we have, for symmetry about the origin, we have something that's kind of, a circle is a pretty common thing to see, or an ellipse is a very common thing to see. And then this one's kind of hard to conceptualize, but essentially what we're doing is now we're kind of folding almost at like if I have a diagonal graph, y is equal to x. If I fold my graph over that and I'm able to mirror my image, then I have symmetry about the origin. So to kind of see these concepts again, I have, that's what I figured out there. And so again, I have this first graph. It appears I do have some sort of symmetry. I have that thing matching up. And it looks as though if I fold the top part of my graph over my x-axis, I will match up the bottom part of my graph. So that is symmetric about the x-axis. It's being flipped over the x-axis. And with this, we have kind of a parabola on our second graph. Same thing again. I'm able to fold my graph over the y-axis, so I have symmetry about the y-axis. And now here's a little bit of trickiness that's going on. So there are things in college algebra where it's like, okay, I showed that this function is, we'll see this later, I show that this function is odd, and I don't have to worry about any other possibilities. That's not true with symmetries. So you can have multiple types of symmetries. So in this case, on this right graph, what we have is, if we look at it, I could fold that graph over the y-axis. So I take the right side, fold it over to the left side, it matches up, boom. I have symmetry about the x-axis. I could fold the top part of my graph over the bottom part of my graph. And I have symmetry about the origin, because if I draw that kind of diagonal line, you might have to be a bit careful with this. But if I draw a diagonal line, I would be able, well, the y equals x, specifically diagonal line, I would be able to fold it over in that one. And with the origin, honestly, I would more likely use the strict definition more, because sometimes my brain messes up when I'm trying to think about folding diagonally. It's not as intuitive, where I can kind of pick some points from this graph here and say, okay, oh, this bottom right point is matching with the top left point. I have my point xy, negative x, negative y. Matches up that way, and kind of find symmetry about the origin. Oh, that's a long-winded way of saying this graph actually has 3 symmetries, and that's perfectly fine. So historically, what the questions that show up on the exam and on the final look like is they'll give you 2 or 3 graphs and say, is it symmetric about the origin, x-axis, y-axis, and you can kind of pick and say yes, yes, no, or all of them are, or maybe you could have a graph with no symmetries, and that's perfectly fine as well. Now, if we are dealing with equations and we don't have graphs, because the graphs are pretty intuitive, which is nice, and if you're really good at graphing, you could take an equation, graph it, and then follow the process we saw in the last slide. But sometimes you have equations like this where I don't know what this graph looks like. And so the process of finding a symmetry kind of falls back more to that definition. So if I want to see if something is symmetric about the y-axis, what I do is I plug in negative x for my x, because I want to see if that point gets mirrored. And if that doesn't change my equation after simplifying, then I have symmetry about the y-axis. So that's very long-winded. In practice, it's actually not that terrible. So I have this equation. I'm going to plug in negative x everywhere that I have an x. Make sure that I put it in parentheses. Now I have to simplify, because right now it doesn't look like they're the same equation, but I'm going to simplify as far as I can. And well, negative x times negative x actually gets me a positive x squared. So that leaves me with 2x squared minus 18 on the top. and x squared plus 4 on the bottom. And now I look back to my original equation. Oh, those match. They're exactly the same now after I've simplified. So this graph is symmetric about the y-axis. Very similar concept when I'm trying to test for symmetry about the x-axis. So I'm using the exact same equation on all three of these examples. What I do is, in this case, I plug in negative y for y, simplify my equation, and if the simplified equation matches the original, I have symmetry about the y-axis. So here I have now my original equation again was y is equal to 2x squared minus 18 over x squared plus 4. I change my y to a negative y, and now to simplify, what I'm going to do is I'm going to multiply both sides by negative 1. So then my equation becomes y is equal to negative 2x squared minus 18 over x squared plus 4. And if I wanted to be extra careful, I could distribute out the negative on the top of my fraction. But spoiler alert, it's not going to change, or it's going to change my equation. It's not going to make it the original equation. And so I would say this is not symmetric about the x-axis. Last process, when I'm trying to, and I guess I just have another typo, if I'm trying to do symmetry about the origin, now I plug in negative x for x, and I plug in negative y for y. So I'm almost combining the two. And so what happens if I plug in negative x for x and simplify? Well, okay, I have negative y is equal to 2x squared minus 18 over x squared plus 4. And that's actually the exact same thing that we saw in the previous part symmetry about the x-axis. So I see here that I can multiply both sides by negative 1 again, but we saw above that that showed that it wasn't symmetric. And so in this case as well, it is not symmetric about the origin. Now, something you may notice, and maybe you want to kind of test this and discover it on your own, I recommend by all means doing that with almost any rule that I say in this course, is that if we don't have symmetry about the y-axis, or if we have symmetry about the y-axis, like in this case, and we don't have symmetry about the x-axis, we're not going to have symmetry about the origin. And there is a little bit more to the patterns. I would recommend kind of testing them and emailing me and checking to see if those are actually always true or maybe kind of a fluke. But there are patterns to this, and there's patterns to, I kind of keep alluding to this, that we'll see in a couple of lectures. Even in odd, don't rely on them. Do the work, go through the process. With any test in this course, if you're showing your work and you make a mistake, you're going to get a lot more points than showing none of your work and making a mistake. So make sure you're going through the steps. Now, for graphing key equations, there's a lot of ways to do graphs. There's a lot of kind of tools we have depending on the type of graph. If we have a line, if we have a parabola, we're going to see all of that. And those are usually much more efficient than what we're going to do here. All of that being said, this concept is pretty universal because it works for any graph. And it's kind of a building block. That's not what we're doing here. Now, for graphing key equations, what we're going to do is we're going to kind of, we're going to become detectives. And we do this again throughout this course. We're going to find as much information as we can, and then once we have all of that information, we're going to draw a graph that is, it might not be exactly correct because that's almost impossible to do with a pencil and a piece of paper, but it's going to be close enough that you can get what the graph looks like, what the concepts are, and kind of get key characteristics about the graph. So since we've already done this in this section, let's go ahead and find the intercepts of this equation. Y is equal to x squared minus 4. In order to find a y-intercept, well, we plug in 0 for x and solve. So 0 squared 0 minus 4 is negative 4. Now I get 0 comma negative 4. Similarly, to find my x-intercepts, I plug in 0 for y, solve for x. This is one of those nice difference of squares equations. So I have x squared, I have 4, which is 2 squared. So I can break those into two separate things, x minus 2, x plus 2. If you don't feel comfortable with difference of squares, really it is just a basic factored problem as well. I want two things that multiply to negative 4, add to get me 0. Those two things are 2 and negative 2. Go through and solve. It's pretty doable. I break it up into two pieces. set them equal to 0, and solve so I get 2 comma 0, negative 2 comma 0. And those are my 3 points. Now I want to kind of see what my symmetries are so that when I'm kind of plotting this graph, I have more pieces of information to make it look more correct. Well, I test my y symmetry by symmetry about the y-axis by plugging in negative x, simplifying. Negative x squared is x squared. Check, good to go. For my symmetry about the x-axis, I plug in negative y, again, kind of multiply both sides by negative 1. Negative x squared plus 4, I go back and check the original equation, not matching up, not going to be symmetric about the x-axis. Now we're going to do the origin. You might be able to probably gather that it's probably not going to be, but let's go through the process. It's always a good idea to go through the process. So now I plug in negative x, I plug in negative y, negative x squared is x squared, and then if I multiply both sides by negative 1, again, I don't have the match to my original equation, so it's not symmetric about the origin. So I have symmetric about the y-axis, and I have my 3 key points. Now, what I can do is I can gain more information by just plugging in values. So here I just came up with a table of negative 2, negative 1, 0, 1, 2. Those are good standards to use if you're trying to kind of build a table. You want to at least have 0 in your table in general, and you want to have a negative number and a positive number. But you could pick negative 4, negative 1, 0, 1, 2, or something like that. You don't have to always pick these points. And so if I take these points, plug them into my equation, negative 2 squared is 4, minus 4 is 0. Negative 1 squared is 1, minus 4 is negative 3. 0 squared minus 4 is negative 4. 1 squared minus 4 is negative 3. 2 squared minus 4 is 0. So if I'm trying to graph, I'm going to plot those key points. Cool, I actually have all of my intercepts on that graph with the table that I built. So I have that, and I also know that I should have symmetry about the y-axis. So if I'm going to connect the dots and draw them, and this line goes on forever and ever, that is what my y is equal to x squared minus 4 is. And really, this example is kind of just we're going to tie up this entire section. We're going to find better ways of graphing, more efficient ways of graphing, but you still should know how to do all of these things in almost any graph. We're going to see time and time again, finding intercepts. You should know how to find your symmetries. And so this is kind of if I were taking notes and trying to review the section to make sense of it, I would make sure this slide makes sense to me, because this is the section. This is all the pieces put together.